Hello everyone. Hope you are doing very well. So today we are going to see the theory part 8 of the chapter 6 Haloalkanes and Haloarenes. So let's begin our today's topic. NCERT chapter 6 Haloalkanes and Haloarenes theory part 8, and specifically today we are going to focus on the section 6.7. This is disclaimer. Objective of today's lecture. After attending this lecture, you will be able to use the stereochemistry as a tool for understanding the reaction mechanism. So today we are going to focus on the stereochemistry to better understand the reaction mechanism. The topics to be covered according to the NCERT in today's lecture: 6.7 section, that is chemical reactions, under which we will study the 6.7.1 reaction of haloalkanes, and then we will also solve an example 6.6. So let's begin with our first subsection 6.7.1 reaction of haloalkanes. So until now we have covered the SN1 and SN2 reaction along with their mechanism, right? Today we are going to first of all see the comparison between the SN1 and SN2 reaction, that is substitution nucleophilic unimolecular and substitution nucleophilic biomolecular reaction. So you can see this table depicting the differentiation between, or the comparison between, the SN1 mechanism and the SN1 reaction and the SN2 reaction. SN1 reaction, substitution nucleophilic unimolecular reaction, follows first order reaction. As I said previously, that for the representation of the substitution reaction, this S is for substitution, N representing nucleophilic, and 1 is representing the order of the reaction. Because it is a first order reaction, so that's why we are writing here as 1. So SN1 reaction follows first order reaction, SN2 reaction follows second order reaction. SN1 reaction is a two-step reaction. Remember, we have seen that SN1 reaction is a two-step reaction. First reaction is the slowest step, which is also the rate determining step. Second step is the fast step, where the carbocation or the nucleophile is attacking on the carbocation to get the product, right? So SN1 is a two-step reaction involving a formation of intermediate. SN2 is a one-step reaction. It doesn't involve any intermediate formation. So no intermediate form in the SN2 reaction. Meanwhile, in the SN1 reaction, carbocation formed as an intermediate in the first step, which is the slower step. For the SN1 reaction, the order of reactivity is from tertiary alcohols to secondary alcohols to primary alcohols, right? So for the SN1 reaction, the order of reactivity is from the tertiary carbocation to secondary carbocation to the primary carbocation. Okay? Because carbocation here forming as an intermediate, and then in the second step, the nucleophile is attacking on the carbocation from either of the side, right? So the stability of carbocation is a key factor on deciding the reactivity in the SN1 mechanism in the SN1 reaction. So that's why we are saying that tertiary carbocation in the SN1 reaction is having the highest reactivity because of its highest stability. Then the secondary carbocation, and the least reactive will be primary carbocation. On the other hand, in the SN2 reaction, there is no intermediate form as carbocation, right? There is a transition state forming. So it is a single step it is a single step reaction where the nucleophile is attacking on the carbon at which halogen is already present. So nucleophile is attacking from the backside of the carbon halogen bond, and then there is a transition state where carbon is simultaneously forming 5 bonds, and the nucleophile and the incoming nucleophile and the carbon bond is forming, and the living nucleophile and the carbon bond is breaking, right? And then finally you will get your final product where nucleophile is finally attached to the carbocation carbon, right? So here, because there is no intermediate form as carbocation, so here the steric hindrance is the key factor in the SN2 reaction, because the incoming nucleophile is attacking from the back side of the carbocation carbon, right? So as the shorter or the smaller group is present on the carbocation carbon, it will be beneficial, right? So that no steric hindrance will be there that will affect the incoming nucleophile to bond with the carbocation carbon. So the order of reactivity in the SN2 reaction will be highest for primary carbocation, then for secondary carbocation, and then for tertiary carbocation. So this order of reactivity in the SN2 reaction is inverse or reverse of the order of reactivity in the SN1 reaction due to its mechanism. Okay. The rate, if you talk about the rate, the SN1 reaction rate is dependent only on the concentration of alkyl halide. So the rate equation will be K times Rx. So here the rate is only dependent upon the concentration of alkyl halide and not the nucleophile. Okay. But in the SN2 reaction, it is a second order reaction. So rate is depending upon both the concentration of alkyl halide and the nucleophile. So rate equation can be written as rate is equals to K times Rx, that is alkyl halide concentration, and the nucleophile concentration. Okay, so this is the difference and the comparison between the SN1 and SN2 reaction that we have understood using this or understanding this table given. Now let's see the stereochemical aspects of nucleophilic substitution reaction. Let's first talk about the optical activity. This is very important topic that we are going to cover in this lecture. Optical activity. Okay, optical activity. So in the certain compounds which are called optically active compounds, they rotate the plane of plane polarized light when it passes through their solution. So what happened? Basically, optical activity is referring to the ability of the compounds to rotate the plane of plane polarized light as it passes through the solution where the compound is there. Okay, so the compound that are able to rotate the plane of plane polarized light, they are called as optically active compounds, and this property is known as, or this ability is known as, optical activity. You can understand through this diagram. If you have an ordinary light and you pass it through Nicol prism, you will get a plane polarized light after passing through the Nicol prism. Okay, or let's say you have a plane polarized light where light is in a particular direction, in a particular plane. Okay, when it passes through the solution where there is optically active compounds present which rotate the plane of this plane polarized light, and you will get a rotated plane polarized light. You can see the plane is rotated at some angle. Okay, so optically active substance or its solution, you can see. So due to the presence of optically active compounds in the solution, when you pass a plane polarized light through the solution, its plane is going to be rotated and you will get the rotated plane polarized light. Plane polarized light is produced by passing the ordinary light through a Nicol prism. Okay, through a Nicol prism, the plane polarized light is obtained through by passing the ordinary light through that prism. Measurement. So what will be the angle of rotation at which the plane of the plane polarized light is rotated? That is measured using an instrument called a polarimeter. The polarimeter we used, which is an instrument we used for measuring of the angle of rotation of plane polarized light. Two types are possible depending upon the sense of rotation. So basically, on the basis of the rotation, that in which sense the rotation is happening, there are two types of rotation is possible, or two types of compounds are possible. First are dextrorotatory. You can also call them as D-form, or you can also put a positive charge for their representation before their degree of rotation. Okay, so they are the compounds which rotate the plane of plane polarized light to the right side. That means in the clockwise direction. Clockwise direction means, like in the clock, if you see the if you start from the 12, very 12, so 12, after 12, the clock will go at the 1, right? After 12 it will be 1 o'clock, then it will be 2 o'clock. So in the clockwise direction, that means in the right direction, if the compound is rotating the plane of plane polarized light, that compound will called as dextro-rotatory. In short form, you call it as D form, or also you can put it as a positive symbol, as a positive sign in before the degree of rotation. So it indicated by a positive sign before the degree of rotation, as I said. Second type is levorotatory, on the basis of sense of rotation. So because dextrorotatory is the compounds which are rotating the plane into the right, that means into the clockwise direction, the levorotatory should be opposite of it. Okay, so levorotatory, which you can also call it as L form, or you can also put a negative sign before the degree of rotation for its representation. So levorotatory compounds are the one which rotate the plane of plane polarized light to the left direction. Okay, that means anti-clockwise direction. Anti-clockwise means the direction in which clock follows, in which clock orders, opposite to that is anti-clockwise. That means from 12 you are going to 11, then you are going to 10 o'clock, and then you are going to 9 o'clock. Okay, that is anti-clockwise direction. So levorotatory compounds are the one that will rotate the plane into the left direction. This is indicated by a negative sign. You can put a negative sign for the levorotatory representation before the degree of rotation. So if you have a plane polarized light, you can get two types of compounds from it. That is one enantiomer, which is rotating the plane of plane polarized light into the clockwise direction. Also, you can represent it by positive sign, so in the positive direction. The second enantiomer you are getting, the other enantiomer you are getting from the plane polarized light, is the levorotatory, which is rotating the plane of plane polarized light into the left side, into the left direction. That is in the counterclockwise rotation. So you can see this is counterclockwise rotation. The point arrow is pointing from 12 to, like from here it is, let's say it is here in this diagram, here it is in 12 position. Then in this positive form, 12 will go to 1, and in this negative form, 12 is going to, this arrow pointing from 12 to 11. This is counterclockwise or anti-clockwise direction. So rotation of plane polarized light by an enantiomer, how it is going to be, that you can see or understand using this diagram. Optical isomers and isomerism. Positive and negative isomers of a compound are called optical isomers. Okay, so for a compound, if you get a positive and negative isomers of that particular compound, that means it's dextrorotatory and levorotatory form. Then they are called as optical isomers of that compound. Phenomenon. This phenomenon is termed as optical isomerism. Okay, this phenomena of optical isomer is termed as optical isomerism. Molecular asymmetry, chirality, and enantiomers. So let's see what are these. Carbon having all different substituents, and the mirror image of the molecule is not superimposed on the molecule is called asymmetric carbon or the stereocenter. What I'm saying? A carbon which is having its substituents which are all different. That means carbon is having 4 valency, it is tetravalence, right? So for completing its tetravalency, it should bind through 4 different substituents, right? It can be same or different. So the carbon which are having all different substituents attaching with it, and also its mirror image is not superimposed, or its mirror image is not superimposable on itself. Okay, then that carbon is called asymmetric carbon or stereocenter. Now let's talk about the chirality. objects that are non-superimposable on their mirror image, they are known as chiral compounds or the chiral. Okay. So any object, let's say you are taking a circle. Okay. You are making an image of that circle, putting a mirror in between. So after putting a mirror in between, you are making a mirror image of that circle. You will obtain the same circle, right? That means you can you can take the image circle and put it on to the initial circle, and it will be same. It can be properly superimposed, right? So the objects that are non-superimposed on their mirror image, they are called as chiral. One of the example is our hands. Okay, if you take our hands and you draw the mirror image of one of our hands by putting a mirror in between. Okay, if you draw the mirror image of our one hand, the image that you will get when you take that image and put as it is onto the previous or onto the initial hand, then it will not be superimposed. Okay, that means our hand images, the initial hand and its mirror image, they are non-superimposable, so that means they are chiral. And this property is known as chirality. Chiral molecules are optically active. Okay, so these chiral molecules are optically active. That means they have this ability to rotate the plane of plane polarized light into some direction. The objects that are superimposable on its mirror image, they are known as chiral. So we just put a before a chiral to show that this is opposite of the chiral. Okay. So the objects that are non-superimposable on their mirror image, they are chiral, and which are superimposable on their mirror image, they are achiral. Achiral molecules are optically inactive. So the achiral molecules don't have this ability to rotate the plane of the plane polarized light into some direction. So they are optically inactive. This is the image, figure 6.4, showing some example or common examples of chiral and achiral objects. So chirality, an object that cannot be superimposed on its mirror image is called chiral. Okay, that means object that cannot be superimposed, that are non-superimposable. For example, our two hands. If you take this one hand, you put a mirror in between and draw its mirror image. Okay, so you know that because this is a thumb, into the mirror image, this thumb will also be like nearest to the mirror, right? In the image also. So you can see this is the mirror image of this hand. Okay, so when you are drawing it and when you are taking this hand, and after taking, you are placing this mirror image of the hand into the previous hand, into the initial hand, then it will not be superimposed, right? So these are chiral. Meanwhile, if you take this glass image or this glass object and you draw the image of this glass by putting a mirror in between, and then when you take this image of the glass and put on this initial glass object, it will be properly superimposable, right? So they are achiral because objects can be superimposed on its mirror image, right? The another example of chiral object is the foot. So you take this foot and you draw mirror image of this foot, and when you take this image of the foot to impose on this initial foot, it will not be superimposed, right? So it is a non-superimposable mirror images. That means this object is chiral. Meanwhile, as I said, the example of circle, you take and you draw a mirror image, and you then take this circle image and put on this initial circle, it will be properly superimposable. So they are superimposable mirror images of this object. So this object is achiral. Okay, so chiral objects here in the left hand side and non-chiral objects here in the right hand side, based on their ability of their mirror images, whether to be non-superimposable or superimposable. Let's take an example in detail. So consider a simple molecule, propane 2-ol. propane 2-ol means we have a 3-carbon chain. At the second position, we have hydroxyl group, that is alcohol group, right? So we are drawing in the 3D structure this A diagram of the propane 2-ol, where this is the carbon, okay, at which there is 2 methyl group present, CH3 and CH3. One is outside from the plane and one is inside to the plane. And there is one hydrogen in the plane. And there is this hydroxyl group, which is also in the same plane, which is in the which is same of the carbon, okay, and the hydrogen. This is the propane 2-ol. Now you put a mirror and draw this propane 2-ol mirror image. Okay, you will get something, this kind of structure, which is B structure, let's say. This is mirror image of propane 2-ol, where OH will be here, carbon will be here, hydrogen and 2 methyl groups are attaching to it. Now, you take this B compound and rotate it by 180 degree. Okay, when you rotate it in the right direction, that means in the clockwise direction by 180 degree angle, you will get this rotated mirror image, which we are calling as C. Okay, where carbon is here, hydrogen, it is attaching to 2 methyl groups and hydroxyl group. Okay, so this is figure 6.5, where B is the mirror image of A, and B is when rotated by 180 degree, we get C, and C is obtained, and C is also what? C is the superimposable on A. C is actually same as A. If you take the C image, like the rotated mirror image, and you put as it is on the A structure, they will be properly superimposed, right? So C can be superimposable on A. So propane 2-ol does not contain an asymmetric carbon. So propane 2-ol do not have any kind of asymmetric carbon. That means there is no carbon present in the propane 2-ol, where all the substituents are present which are different, right? So there is in the propane 2-ol, it is not containing any asymmetric carbon. And the mirror image, which is B, which you have drawn using the A image or the A structure. So the mirror image B is not overlapping with the structure A, right? If you take this B mirror image and if you put it on the A structure, it will not be superimposed, right? So the mirror image B is not overlapping with the structure A. But if you take this rotated mirror image C, it will overlap with the structure A. So propane 2-ol is an achiral molecule. Okay, propane 2-ol is an achiral molecule. You can also check that all the substituents are not different, so it is achiral. Okay. If we consider another simple molecule, which is butane 2-ol. Here, butane 2-ol, that means 4 carbons are there, and the second position we have hydroxyl group. Okay, it is a structure of butane 2-ol, which we are calling as D structure. Okay, now again the simple thing, that carbon at which the hydroxyl group is attaching, it is attaching with methyl group, ethyl group, and one hydrogen and one hydroxyl group. Okay, when you put a mirror, it will form its mirror image. So mirror image of butane 2-ol, which we are calling it as E. So E is the mirror image of D, and when E is rotated by 180 degree, you get F, which is a rotated mirror image, and F is non-superimposable on its mirror image D. Now, if you put this F rotated mirror image on the structure of D, that is butane 2-ol, it will be non-superimposable, right? So butane 2-ol has 4 different groups that are attaching to carbon. So there is a carbon in the butane 2-ol which is attaching to 4 different groups: methyl, ethyl, hydrogen, and hydroxyl group. And mirror image that you are getting, that is E, and rotated mirror image that you are getting, that is F, after the rotation of 180 degree. That means after the plane polarized light has been passed through it. The F does not and the E does not overlap with the original structure D. So butane 2-ol is a chiral molecule. And you can also see the carbon at which hydroxyl group is present. It is having all the substituents which are different: methyl, ethyl, hydrogen, and hydroxyl, right? So it is a chiral molecule because chiral carbon is present in it. So butane 2-ol is a chiral molecule. Enantiomers. Now, let's see the enantiomers. Stereoisomers that are non-superimposable mirror images of each other. So enantiomers are those stereoisomers that are non-superimposable mirror image of each other. Until now, I hope you have understand the meaning of non-superimposable mirror images. So enantiomers possess identical physical properties. For example, melting point, boiling point, also the refractive index. So enantiomers possess identical physical properties. They differ only in the rotation of plane polarized light. Okay, so enantiomers are different from each other only on the basis of rotation of plane polarized light. That means one isomer is dextrorotatory and the other isomer is levorotatory. For example, if you take the enantiomers of lactic acid, let's see. So we have the structure of lactic acid. The one is levorotatory and the another one is dextrorotatory. How we identify that? You are putting a negative sign. That means it is a levorotatory. It can rotate the plane of plane polarized light into the left direction. And the other structure is a dextrorotatory structure because it can rotate the plane of the plane polarized light into the right direction. And these two mirror images, this red line is showing the mirror. These two mirror images are non-superimposable mirror image. That means if you take this mirror image, the dextrorotatory one, and put it onto the levorotatory structure, it will not be superimposed. So they both are non-superimposable mirror images of lactic acid, and they are the enantiomers. You can call them together as enantiomers. Okay, so enantiomers are stereomers that are non-superimposable mirror images, and they differ only in the rotation which they do of plane polarized light. Okay, one is levorotatory and the other one is dextrorotatory. Racemic mixture. Now let's understand the racemic mixture. You can also say racemic modification. A mixture that contains two enantiomers in the equal proportion. So the mixture that is having two enantiomers in the equal proportions, that is known as racemic mixtures. So this racemic mixture has zero optical rotation. That means rotations of one isomer cancel out the rotation of other isomer. So the total optical rotation of the racemic mixture is 0. For example, the racemic mixture of lactic acid. So we have this lactic acid where this is R lactic acid and this is S lactic acid. Okay, so the two enantiomers in the equal proportions, 50% and 50%, and they are in a same mixture. So that mixture is known as racemic mixture. Two enantiomers in equal proportions, one cancel out the other optical rotation. So the whole racemic mixture will get zero optical rotation. Okay. Racemization. Now, the process of converting an enantiomer, or you can say conversion of enantiomer into the racemic mixture. Okay, conversion of enantiomer into the racemic mixture is known as racemization. Now let's talk about retention. So they are important terms, okay, that will help you in understanding the stereochemical aspects of nucleophilic substitution reaction. So understand them very, very carefully. So next important term is retention. Retention of configuration. What does it mean? preservation of spatial arrangement of bonds around an asymmetric center. Where we have a asymmetric center, that means the carbon having different substituent around it and it is asymmetric, it is stereo center. Then how the retention or the preservation of spatial arrangement of the bonds is going to be there around that asymmetric center. That is, we are calling it as retention of configuration. So in a reaction, when the reaction is happening and around an asymmetric center, the spatial arrangement of bonds is preserved even after formation of products. That factor is known as retention or retention of configuration. You will understand it by looking at an example. We will see. So this occurs during a chemical reaction or a transformation or a chemical transformation. You can understand better through this reaction. So see, this is a negative 2-methylbutane 1-ol. That means levorotatory or levio 2-methylbutane 1-ol. Okay. So we have CH3, CH, CH2, OH, CH2, CH3. We have this chain where at the second position we have methyl okay. So this is a chain where at the very first position, that means at the very first carbon we have hydroxyl group attached, at the second carbon we have methyl group attached, and then there is this third carbon and this is fourth carbon. So 4 carbon chain butane. Okay, so 2-methyl at the second position we have 1-methyl, butane 1-ol at the first carbon we have hydroxyl group, and negative sign is representing the levorotatory form. So this is having an asymmetric center, which is this carbon, at which, that is the second carbon, at which methyl group is present. Okay, so the reaction is happening of this alcohol with hydrogen chloride. Okay, so what will happen? This halogen is going to replace this hydroxyl group present in this alcohol, right, and give you an alkyl halide. So after heating, you will get this product, positive 1-chloro-2-methylbutane. That means at the first position you will get the chlorine, at second position the methyl will be same, and there is butane chain. Okay, plus H2O as a side product you will get after the addition of hydrogen and hydroxyl group, right? The positive sign is representing that this product is dextrorotatory. Now if you understand this, we are calling this second carbon as asymmetric center. This is stereo center or asymmetric center. Now the spatial arrangement around this asymmetric center, okay, spatial arrangement of bonds is preserved. You can see in the reactant, this asymmetric center has 1 CH3, 1 hydrogen, 1 CH2 and something like hydroxyl, and then CH2, CH3. And the same is happening, same spatial arrangement of bond is present in the product also around this asymmetric center, asymmetric carbon. That carbon is having 1 CH3, 1 hydrogen, CH2, CH3, and this CH2 and chloride, right? So the bond are same, the spatial arrangement of bonds are same around this asymmetric center even after the formation of product. So we preserve the spatial arrangement of bonds around the asymmetric center, and this fact is known as retention of configuration. The conditions for retention: no bond to the stereo center is broken during this reaction, because we have to preserve the spatial arrangement, right? So no bond should be broken during the reaction when there is retention. So you can see in this reaction also, around this asymmetric center, no bond is breaking, every bond is preserved. Product retains the same general configuration of groups as the reactant, and in the product, the general configuration is same of all the groups that are present around the asymmetric center that is already present in the reactant. So the product is retaining the same general configuration which is present in the reactant. So there is an important note that same configuration at asymmetric center is present in the retention of configuration, but optical rotation sign can change, because you can see Levio is converting to dextro, right? So configuration of groups we are getting same at the asymmetric center, but the optical rotation sign can change from the Levio to the dextro or vice versa. So different compounds having same configuration can have different optical rotations. One dextro and other may be Levio. Now let's move to the next important topic: inversion, retention and racemization. So you can see this diagram where we have this product at the very center, where carbon, we have asymmetric carbon attaching with C2H5, ethyl group, hydrogen and methyl group and X group. Okay. So when you are adding Y into it, we are obtaining different products. When you are adding Y into it, you are getting this A product where the X is replaced by Y. Okay. And Y is attaching now with this asymmetric carbon. Similarly, when you are adding Y in, you are getting this other kind of product, that is B, where the spatial arrangement has been changed around this asymmetric carbon. And the third way is when you are adding Y into this main product or main reactant, you are getting the A plus B, that means A and B, both the molecules, both the compounds as your product. What we want to understand, so three outcomes at asymmetric carbon is possible when a bond to it breaks. Okay, so when the carbon which is asymmetric and the bond which is forming at the asymmetric carbon gets break, three outcomes of this product can be possible. First is retention of configuration. So only the compound A is obtained after the retention of configuration. You can see the configuration around the asymmetric carbon is same. Okay, so the configuration remains same. The general configuration of groups around the asymmetric carbon remains same in the A product. So only compound A is obtained during the retention of configuration. The configuration is preserved in this case. Second outcome is inversion of configuration. Inversion of configuration means configuration inversed. So only B compound is possible in that case, or only B compound is obtained. You can compare the main product, main reactant with the product B, that the geometry or the spatial arrangement around the asymmetric carbon is reversed, is inversed in the B. Okay, so when the inversion of configuration is the outcome or is the case happening, then only you are getting compound B. You are only obtaining the compound B where the inversion of configuration is happening as compared to the main reactant. And the configuration is reversed. So in this case, the configuration is reversed. In the first case, where we are obtaining A product, the configuration is preserved. While in the second case, where there is B compound we are obtaining, the configuration is reversed. Okay, so when you are breaking this carbon, asymmetric carbon bond with the X substituent, and you are replacing the X with Y, both outcomes are possible. Where the configuration is preserved, you are getting A product, and where the reversion of the configuration is happening, you are getting the B product. Now we talk about the third outcome. So for the third outcome, racemization is happening, where 50:50 mixture of A and B both are obtaining. That means inversion and the preservation of the configuration, both kind of products we are getting in the ratio 50:50. So the product is optically inactive. And the isomers, the one isomer is cancelling out the optical activity or the optical rotation of the others, right? So the isomers are cancelling out the optical rotation of each other, and you are getting a racemic mixture. The racemization is happening in the third outcome. So these three outcomes are possible when the bond around the asymmetric carbon is breaking. Stereochemistry of SN2 reactions. So we have seen the SN2 reaction, right? So if you talk about the stereochemistry, the products that are forming have inverted configuration compared to the reactant configuration. How? So nucleophile in the SN2 reaction attacks from the side that are opposite to the leaving halogen or the carbon halogen bond, right? So nucleophile is attacking from the opposite side. So back attacking is happening in the SN2 reaction. For example, you are having this halide, that is haloalkane, right? And the nucleophile is attacking from the opposite side of the living halogen. Okay, so this nucleophile OH negative is attacking from the opposite side of the carbon halogen bond, and due to this, the configuration of the product will be inverted. Okay, this is a single step reaction happening only in the single step, and due to the back attacking of the nucleophile on the carbon, the configuration you are getting for the product is inverted from the reactant configuration. So SN2 reactions of optically active halides causes inversion of the compounds. If we talk about the stereochemistry of SN1 reactions, SN1 reactions are accompanied by racemization. How? So reason is that the carbocation intermediate. So SN1 reactions happens in the two step. The first step is the slowest step where carbocation formation happens. More stability of carbocation, more stable carbocation form, more will be the reactivity, right? So carbocation intermediate that is formed in the slow step is sp2 hybridized, and also it is planar. That means it is achiral. So nucleophile here in the SN1 reaction can attack from either side of the planar carbocation and can attach from the either side to the carbocation carbon. It will lead to the mixture of compounds. One product with same configuration. So nucleophile attacks the same side as the halide left. Okay. One product you will get in the mixture, one product you will get which is having the same configuration as the reactant. How? Because in this case, the nucleophile is attacking from the same side, the side from which halide is living. And the other product you are getting in the mixture is having the opposite configuration from the reactant, because in this case, nucleophile has attacked from the opposite side to the living halide group. Example, you can see these two reactions. The first reaction is carbocation formation of this from this haloalkane. The bromine, that is living group, left from the reaction, and you will get a carbocation. Now this carbocation is sp2 hybridized and planar. So nucleophile that are attacking can attack from either side of this planar carbocation, right? So it can attack from this and here from the both side. The OH negative can attack on this carbocation from both side and can lead to the mixture of products, which is positive butane to all and negative butane to all in this example. In the positive butane to all, you are getting this configuration, which is actually having the inverse configuration from the reactant, right? Because the nucleophile has attacked opposite side from the to the opposite side of the carbon from the side where halogen is living. Okay, so that's why we are getting the opposite configuration from the reactant configuration. Okay, so opposite configuration of reactant, opposite configuration of product we are obtaining. So one product we are getting of opposite configuration. The another product we are getting is of same configuration as compared to the configuration of reactant. Why? Because in this case, nucleophile has attacked same side from the side that from where the halogen is living. So you will get a product where the configuration is same as compared to the reactant. Okay, so you will get both the compounds, both the products, the positive butane to all, the negative butane to all. Okay, so similar formula, different structure. You can say spatial arrangements are different, and one is dextrorotatory and another is levorotatory. So you are getting racemization. So SN1 reaction is accompanied by racemization. That's why we are saying, because we are getting both kind of products. You are getting enantiomers as your products. Okay, one product with same configuration and one product with opposite configuration compared to the reactant configuration. Okay, let's solve an example. Example 6.6. The example is that in the following pairs of halogen compounds, which would undergo the SN2 reaction faster. So we have given these compounds, and you can say these pairs. You have to tell that in these pairs, which of the halogen compound would undergo SN2 reaction faster. The first pair is of this cyclohexane, where at one carbon we have CH2Cl. So, and the another is this cyclohexane, where at first carbon we have only Cl. That means chlorocyclohexane. Okay. The another pair is this so butane, or you can say iodobutane, and second is chlorobutane. Okay. So we have these two pairs, and you have to select the halogen compounds from these pairs, which will undergo the SN2 reaction faster comparatively from the another compound. So you got some time, try to solve this question, this example, and then we will see the correct answer. Let's see. So for this example, the rate of reaction for the SN2 depending upon the steric hindrance. Remember, because SN2 is a reaction which happens in a single step, right? And here there is this transition state forming, and nucleophile is attacking on the carbon from the opposite side of carbon halogen bond, right? So the rate of reaction here in the SN2 reaction depending upon the steric hindrance, so that incoming nucleophile will not like face any kind of steric hindrance. If there is more steric hindrance, the rate of reaction will be slower. It will be difficult for the incoming nucleophile, to attack on the carbocation carbon and form the bond. So order of SN2 reaction is, the primary halide will be the preference, or will be highest active, then secondary halide, and then tertiary halide. Primary halide because the steric hindrance will be lowest in this. The larger groups present on the carbocation will not be there in the primary halide. Meanwhile, in the tertiary halide, there can be larger groups attached on the carbocation carbon, which will cause the steric hindrance to the incoming nucleophile. So these two compounds given in the two halogen compounds given first pair is these compounds, in which one is primary halide, where chlorine is attaching, or chlorine halogen is attaching with the carbon, which is attaching with only other one carbon. So this is primary halide. Meanwhile, this another halide is a secondary halide, because chlorine is attaching with the carbon, which is bonding with another two carbon. So in as per the order of SN2 reaction, the primary halide should undergo the SN2 reaction faster compared to the secondary halide. So primary halide will goes faster SN2 as compared to the secondary halide. Okay, so this first halogen compound given here, which is primary halide, will undergo the SN2 reaction faster. Now, if you talk about the second pair of the halogen compounds, we have the same structure, but only the halogens are different, right? Iodobutane and chlorobutane. If you go down the group in the halogens, the size of atom increases. And with the increase in the size of atom, the bond length between the carbon and the halogen is also increasing, due to which the bonding is become weaker, and it will be easy to break the bond, and the reaction will be faster. because the replacing of that chlorine or iodine by the nucleophile will be easier because bond can easily break, right? So size of iodine is greater than the size of chlorine as per the group of the halogen, right? So the iodobutane will show the greater reaction rate than the chlorobutane in these two halogen compounds towards the SN2 reaction. So carbon iodine bond will break easily and the iodobutane will undergo towards the SN2 reaction faster. So iodine will be released as the faster rate, and iodine will be acting here as a better living group. It can faster the rate of living of the iodine from this butane or from this iodobutane will be faster, and you will get a nucleophile on which the nucleophile will can attack. Okay, so SN2 reaction will be shown by the iodobutane very faster. Okay, due to the better living group present, that is iodine. Okay. Let's see the summary. We have covered the optically active compounds. They are the compounds that can rotate the plane of plane polarized light into the left or the right direction. Optically inactive compounds, the inverse of optically active compounds, they does not rotate the plane polarized light. Chiral objects are those that are non-superimposable mirror images. Achiral objects are those that are superimposed, that can be superimposed on the mirror image, okay, on its mirror image. So they are non-superimposable mirror. They are superimposable mirror images. The achiral objects are superimposable mirror images. You can better understand through this diagram, which we have understood the figure 6.4, some common examples of chiral and achiral objects, where the chirality, the object that cannot be superimposed on its mirror image, is called chiral, and the left hand side showing the chiral objects, non-superimposable mirror images, and the right hand side showing the non-chiral objects, superimposable mirror images. Enantiomers we have talked about, which are stereomers that are non-superimposable mirror images. That means they are chiral objects. The example of that is lactic acid, levolactic acid, and dextrolactic acid. They are non-superimposable mirror images. Then we have talked about the racemic mixture, the mixture of two enantiomers in the equal proportions. So one of the example is this racemic mixture of lactic acid. Racemization is a process of conversion of enantiomer into the racemic mixture. And also the racemic mixture has zero optical rotation. Retention we have seen, which is actually the preservation of configuration. And inversion is the reverse of configuration. The configuration gets reversed or inversed. Compound A and compound B are showing the retention and inversion in this diagram. Okay. Compound A is showing the preservation of configuration, that is retention. And compound B is showing the reversion or inversion of configuration, that means inversion. SN1 reaction are accompanied by the racemization, and SN2 reaction are accompanied by inversion of the configuration. Okay, so these are the concepts that we have covered today majorly. Okay, thank you so much. That's all for today's chemistry session. Thank you.